So this paper is really hot stuff. I mean, it's cited every other day. So string theorists write a lot of papers, and they apparently like this one. It was the lead story of the Science Times. The day after that story appeared, it was the second most read story in the entire New York Times website. So string theorists are popular. This is an illustration that came with this. So I was like, I saw this in the New York Times, and I was like, why haven't my colleagues told me about this? So I went and read looked at the paper and tried to read it. And it was pretty extraordinary. I mean, it's like college level equations, like thermodynamics, and there was a section on polymers, and then all of a sudden he said, so that's how you get Newton's laws. And then he went on and got Einstein's field equations. It just, there wasn't a lot of derivation or any kind of rigor. It was just a lot of words and some equations I knew, and then suddenly some amazing claims. And the New York Times article, they said that other string theorists said, it's a really amazing and influential paper, mostly because most of us don't really understand it. So, I mean, this is serious business. This is what's motivating us, so we really have to take a look at it once in a while. So Stein not only noticed this analogy and talk about the similarity, but finally do away with gravity as a fundamental force. So this is, and then in the conclusions, he says that the profound nature of these questions, in our view, justifies the heuristic level of reasoning. Like I said, this is a theory like we've never seen it before. When you're making a profound statement, theorists generally say you need to back it up with rigorous calculations, but not if you're doing string theory. The assumptions we made have been natural. They fit with existing ideas and are supported by several pieces of evidence. So I asked my colleagues at Penn, like, is that really true? They said, oh yeah. So then I realized this evidence is what's called the holographic conjecture, which has nothing to do with reality or our universe or any connection with data, but it's this elegant and theoretically somewhat compelling conjecture. So, anyhow, this is how people talk. So, I mean, we really need to ask why is nobody else working on quantum gravity that's different from string theory? Anyhow, I wrote this down and then I was like, this sounds like pretty similar to what you might recommend for Sarah Palin. Anyhow, I hope I don't sound annoyed or bitter with string theorists. I'm not really. I like them. The nice thing is that on the other hand, our theorists, Richard Massey, he figured out how to get the lights on, and Nick and others are out building telescopes and stuff. And then we had a problem with the window, and it was pretty serious because you couldn't hear the speaker. And our resident theorist, Mr. Hirata, stepped up and fixed it. And moreover, astrotheorists are pretty nice and modest too. I mean, Chris readily agreed when I told him that fixing that window was definitely the biggest contribution he made to this conference. You wouldn't have that with string theorists. Anyway, enough talk about theorists. What do we know about gravity? On small scales, by cosmological standards, we know quite a lot. On millimeter scales and solar system scales, we have constraints at the level of 0.1% or 0.01%. So from millimeter to AU scales, gravity is very, very close to general relativity, spectacularly successful, elegant, simple theory. That's why we haven't heard too much talk about modified gravity between the Second World War and 10 years ago. On astronomical scales, we don't know a lot. I'll talk more about that later. The other place we know about gravity is at early times on horizon scales from nucleosynthesis and the CMB. So at least the Friedman equation and the gravitational constant are consistent with what we know today and with general relativity at the several or 10% level at these epochs in the universe. So those are the constraints, which leaves this huge piece of wiggle room, which is low redshift and large scales. And that's where we're interested in cosmic acceleration. Right? So the spirit of modifying gravity theories is that you want to come up with a theory which matches the solar system and whose homogeneous solution gives you the right distance redshift relation so that it more or less agrees with lambda CDM. Lambda CDM with lambda 0.7. The place where you can get larger departures is in the study of perturbations, namely the metric potentials that we'll see phi and psi, and density and velocity perturbations. So delta and theta, which is a scalar constructed out of the velocity by its divergence, are scalar perturbations that describe the critical structure. So these are altered, and so that's the way that we can use large-scale structure, and it's quite fun because you really need to go back and reinterpret large-scale structure to be able to do tests of gravity. Where the transition occurs, so these theories modify gravity on large scales, they get to GR on AU scales, well that's a lot of orders of magnitude in the length scale, so it's an open question how and why this transition occurs. So this is sort of one of the very few takeaway slides from this talk. So you can think about a pretty simple formalism to think about modifying gravity and how to test it. So here's a very general metric which includes any kind of scalar perturbations, where psi and phi are the metric potentials that can depend on space and time, and that's how they describe perturbations. This is a Poisson-like equation which you can think of as arising when you linearize any kind of or a very broad class of modified gravity theories. Its difference from GR is that we are writing the two potentials psi and phi separately, whereas in GR they're equal. And so instead of 4 pi g, you have an 8 pi g, and moreover g is not a number, but it can be a function of space and time. The relation of the two potentials can be used to set another function, eta, which can also be space and time dependent. Okay, so this is an effective description of a broad class of modified gravity theories at linear level in the potentials. Not the density, it can certainly produce nonlinear clustering, but in the potentials. So the usual equation for the growth of structure at linear orbit, now linearizing in density also, looks like this, where instead of a 4 pi g over here, we have 8 pi g effective over 1 plus eta. So this term contains all the modifications. If g and eta are scale dependent, then you unavoidably get a scale dependent growth of structure even in the linear regime. And you almost always get a time dependence that's different from lambda c. So the linear growth factor d sub delta is modified, and moreover, through these relations we'll see that the growth factor of lensing, which is sensitive to the sum of these two potentials, has the additional modification due to g effective and non-relativistic dynamics, namely the motion of stars and galaxies, is driven by this potential psi. And so that now differs from the potential that's driving the behavior of photons and lensing through this combination of the metric potentials. So that's immediately quite interesting. It means that these different growth factors which are given by the same integral over the expansion rate for dark energy, are now different, tell us different things. They tell us about that kind of an integral over the expansion rate, but also this other stuff. So this description is valid on scales of interest to large-scale structure. You need to do a little bit more to go to superhorizon scales, and you need to do a lot more when you get to scales below the scales of halos, of galaxies and clusters. So we'll look at that as well. Okay. Any questions?